Okay, welcome back, everybody. Couple of things first. Let me share with you what we have left with respect to the schedule. And all right. Okay, so this is our, what is left. Today's the 26th. What I plan to do is actually finish the last two chapters today. We're like on chapter 14, slide 11. We'll finish that up. Chapter 15 is very short, and we'll finish that up, which means that, and I'll put a note in here, on the 3rd, we will basically have what I call a study day. So it'd be open, I'll be here, and it'll be open to, if you have any questions, feel free to drop by. I'll be here about an hour, and if no one shows up, I'll go ahead and shut it down. But, hold on, let me let Ashley in. Okay, so that will be a study day starting the 3rd. All right, assuming we get done with both chapters today, which I don't foresee a problem knocking that out. What we have left is disregard that online lab that's been removed. Okay, we're going to delete that. Yes, do it right there. Okay, and then we'll have the solutions lab this Friday. Okay, I also sent an email with what to expect on the practical, which is on the 5th. And it's basically 10 stations, very short steps of things you've done already in the lab. You measure something, something related to what you've done already, and just fill it in and the answers and submit it. We're good to go. We're done with that, which means that after the exam on Wednesday, don't forget that one, chapters 13 to 15. That means on the 10th, we'll have a Zoom review or study day, if you will. And then there's no lab on the 12th. And then there is the final online that we do on the 12th. Also, the 12th would be the makeup labs for those who need to makeup lab. We're trying to get that set up with the lab people, making sure all the chemicals are there. So that's where we're at. Okay. That also, the 12th, that day is also the last day to submit any late assignments that were not completed. Those assignments can be completed. Used to be the ones that were online used to give you a penalty if they were late, but for some reason this semester Canvas, not only for this class but for other classes, did not set that up properly, didn't work. So there's no penalty for any late assignment. So keep that in mind, the 12th last day to turn anything in. And then also the nomenclature exam, I think 3 of you have reached at the minimum the 80%. Keep that in mind, that exam can assist you, especially if you're on the border with respect to a grade. It can either help you push up, get out of the grade bracket you're in, or it can bring you down. Okay, so keep that in mind. All right, any questions? Everybody know where we at? What to expect?
On the 12th, that makeup lab, is that just like the same hours as like our normal lab?
Exactly, same hours as our normal lab time period. Okay. So I'll also send out a summary on that too. Let me make a note to self. Makeup lab hours, and then study days. Okay. All right. Any other questions? Remember, we did do the chapter 16 back in the lab when we were doing the talk about the gases from the lab on the gases. But chapter 16 will not be on the final exam. Chapters 1 through 15 will be on the final exam and comprehensive. And there are roughly 60 questions. I think there's like an hour and 50 minutes allotted time. So give yourself plenty of time to complete the final exam. Okay. All right. Any other questions? All right, then. Well, let us continue where we left off. My notes say that we were finishing up on slide 11 of chapter 14. Let me rehash what we were talking about. We have been talking about, at this point, about intermolecular forces. We specifically four. Okay, there are 4 types of forces, which we talked about. The London dispersion forces, which are assigned to those molecules that are nonpolar. Okay. Then we have what are called dipole-dipole forces, which are assigned to those molecules that, one, are polar, but specifically are not related or do not involve the use of hydrogen bonded to either nitrogen, oxygen, or fluoride, because those examples, those 3 types of bonds, are assigned a very unique force, which is called hydrogen bridging force, which is of the 3 the strongest force that there is. Okay, so all other dipole compounds, which are, of course, they have to be polar molecules, are assigned dipole-dipole forces. And then finally, the 4th one, which really is a solution that contains an ionic compound, in 9 times out of 10 is an aqueous system, like water. So the ion comes from the ionic compound, and the dipole comes from the aqueous system that has, this is basically, which has a dipole in it. Okay, so those are the 4 forces. We went and talked about dispersion forces, which are basically essentially temporary. Okay, they are induced dipoles. That is because the electrons of one nonpolar molecule, when they come together, are essentially, when they come close distance to each other, the negative electrons of one element then pushes away the electrons of another element to form a temporary partial positive section on one of the molecules, and the other one has a temporary partial negative section. So those 2 would attract to each other. But again, as I stated, they are temporary forces, and these forces are extremely weak. This dashed line is supposed to demonstrate or show that is the attraction between the partial positive part and the partial negative. They attract each other, and there is an attraction, and that's the force. Okay. Now, with respect to dipole-dipole, obviously, it had to be polar molecules. Okay, like for example, HCl, that we also talked about this. This has a permanent dipole. Permanent in that the bond between hydrogen and chloride, there is not an equal sharing of that bond, because the electronegativity of one of the elements is much greater than the other. In this case, the electronegativity, which is a measure of the affinity of an atom to pull electrons onto itself while it is bonded to another atom. So chlorine or chloride here has a lot more electronegativity than the hydrogen. In essence, pulls the electrons toward itself, increases the electron density around the chloride, leaving a permanent partial negative region, which then results on the other end, because all the electronegativity is being pulled away, we end up with a partial permanent positive area. Okay, So as if like like a magnet, we got a north and a south pole, if you will. Well, the negative will attract the south to the partial negative, will attract itself to the partial positive of another molecule, resulting in this interaction. Okay. Now, this interaction denoted by the dotted line is much stronger. This force is much stronger than the London forces we just talked about. And they are more permanent. It is a permanent attraction, a permanent dipole, unlike the London forces, which are temporary. Okay. All right. Now, with respect to hydrogens that are bonded to either nitrogen, oxygen, or fluoride, we have it is a dipole-dipole force. However, it is a force that is a little bit stronger than simply a dipole-dipole. And that category is such that it even has its own name, which is the hydrogen bridging force. Okay, hydrogen bridging force, which again, I repeat, it is a dipole, but it's a dipole with a little bit greater strength than the regular dipole. And it's called hydrogen bridging. Also, the name you may hear or see someplace called hydrogen bonding, trying to do away with that name because it's not a true bond. It's still an interaction. And so here we have a hydrogen, which is bonded to oxygen, and therefore there's hydrogen bridging. And that attraction is there between the permanent dipole between the hydrogen and the oxygen, which is a partial positive and a partial negative, respectively. Okay, it's attracted just like the dipole-dipole to another molecule that has the same dipole. Okay, but that attraction is a lot stronger, requires a lot more energy to break up that attraction. All right, so that is the hydrogen bridging force. Okay. And this is where we ended up. So you can see here water molecules, all of them interacting with each other in solution. And, it three-dimensionally, because normally when we display something, we tend to think, it's a two-dimensional display. But keep in mind, in the real world, if you will, our world is such that it's a three-dimensional X, Y, and Z. So these forces are quite strong all the way around the axis. Okay. Finally, the last force is an ion dipole force. And like I stated, we have an ionic compound, okay, which is normally put in solution. Whether it's totally soluble or insoluble makes no difference. The fact is it's still ions in solution. Obviously, if it's classified as insoluble, the bulk of it is out of solution, but it still has ions in solution, small amount. Okay, as we talked about when we went over the solubility rules. And if it's soluble, then totally all the ions go 100% in solution. So what we have here to depict that phenomena is you got the sodium ion and surrounded by molecules of water, specifically the partial negative aspect of water, which is the oxygen, which is solvating the positive fully charged positive charge of the ion. Now, on the other end, you would have the chloride interacting. So change. Okay. Over here on the other end, you would have maybe if this were, for example, sodium chloride in solution, and then the chloride would be solvated with the positive part of the partial positive part of water. So this whole setup would be totally solvated, and that is how the ions are dissolved in water. This picture here kind of shows, demonstrates what I just talked about. You got the crystal sodium chloride. Then we dissolve that crystal sodium chloride in water. You get the water molecules, looks like Mickey Mouse ears here, right? It's totally the solvated, the sodium ion, the sodium cation is solvated with the negative part of the water, and then the positive, partial positive part is solvates the chloride, okay? All right, so to summarize all this with respect to bonds versus forces, okay? We have talked previously about the bonds. We have simply two types of bonds. Okay, and that is the ionic bonds, which is the requirement is you got to have a metal and a non-metal combination. Okay, in that aspect, with respect to ionic bond, you have a full charge, full positive, full negative. These are ions that come together. The other type of bond is the covalent bond, that we have sharing of electrons in the bond. We either have equal sharing or unequal sharing. If it is unequal sharing, because of the differences of electronegativity between the atoms that are being bonded, you have an unequal sharing. We ended up with a polar bond. We have a permanent dipole on that bond. Then if there's equal sharing, simply again, because what is bonded together has the same electronegativity, and there's no pulling of electrons more from one atom to the other, it's just equally pulled. We have a nonpolar covalent bond, okay? Those are the bonds. With respect to forces, we have four forces. London forces, which are assigned only to nonpolar molecules. Then you have a dipole-dipole force, which is assigned to polar molecules. And the hydrogen bridging is also assigned to polar molecules, but specifically assigned to hydrogens that are bonded to nitrogen, oxygen, or fluoride only, okay? If that's not the combination, then it defaults back to dipole-dipole. And then the last force is the ion dipole force, which results in using an ion in some polar molecule, which, like I stated, 9 times out of 10 is a water solution aqueous system. So in order to assign the molecule, we have to first define. Let me restate that. In order to assign a specific force here, we have to define the molecule and determine whether the molecule itself is polar or nonpolar. Now, quick refresher on that. Let me share with you whiteboard here. Okay, so when number one, when all bonds are nonpolar bonds, okay? When we have nonpolar bonds, that implies that the molecule is nonpolar, okay? Once we determine that, then the only force that molecule is given is the LDF, London dispersion forces. Now, this is also pertains to hydrocarbons. Okay, hydrocarbons are those that have nothing but carbon-hydrogen bonds. Okay, and those that have all the diatomics that have nonpolar bonds. Okay, and so they're automatically defined as nonpolar. They automatically the only thing they have to deal with forces is London dispersion forces. Now let's talk about polar bonds, because even though you have polar bonds, you may or may not have a polar compound or molecule, okay? And here's a scenario where you have a polar bonds, if you will, bonds are bonds, but the molecule is nonpolar. Okay. Now we did way back when with Lewis dot structures. In order to determine this, you refresh your memory on doing Lewis dot structures. Recall we added up all the valence electrons, told you what was the central atom, and we bonded all the atoms to the central atom, and then it made bonds with the valence, total number of valence electrons we had. Okay, and then we moved the bonds around to create double bonds if we didn't have enough, to make sure that everybody had the octet fulfilled. Okay, except for hydrogen, which always only has one bond, no other electrons around. Well, we had done carbon dioxide. When we did carbon dioxide, we ended up with the Lewis dot structure as follows. We ended up with this is carbon dioxide. Okay. We ended up with a general formula of AB2. We called that how we did that, which gave us the geometry of being linear. Okay. Now, if we look at the molecule, the way the geometry is set up, we have a carbon-oxygen bond. Well, there is a polar bond. That is a polar bond. Specifically, that polar bond is pointed toward oxygen because oxygen has a higher electronegativity than carbon. Okay, so we do have a polar bond going in the right direction, to the left to right. We also have on the other side another polar bond. So in this case, we have two polar bonds. Okay, and you might think that, okay, I got two polar bonds, the molecule is going to be polar. Well, that's not always the case. If the polar bonds are directly opposite of each other, which they are here, because the one on the right is going from left to right, is going in the positive direction. Okay, if we use that axis that how we normally can use for scale, we got 0 in the middle, right? Up is positive, to the right is a positive direction, down is negative, and left is negative with respect to magnitude. Well, these arrows represent what are called vectors. It's not important here other to say that that arrow represents a magnitude, a value, and a direction. And so we can graphically look at the direction and determine if they're going to cancel each other out. Since it's a carbon-oxygen bond on both sides, the magnitude on both sides is the same. We don't have to give it a number. We just know it's the same because it's the same type of a bond. Okay. So this one is going from left to right is positive. The other one is going from right to left. It's going in the negative direction. Because of that, both bonds cancel each other out because they're going in completely opposite directions. And the net effect is the polarity, the bonds cancel out. The net effect is that this molecule is nonpolar, okay? Because the polar bonds cancel each other out. All right. That being the case, since carbon dioxide now is defined as nonpolar, then we can assign to it very quickly the London dispersion forces. All the other forces do not pertain to carbon dioxide because of the polarity of the molecule. The other scenario is you might think that you end up with something like carbon dioxide, but it's different. Sulfur dioxide. If we do the Lewis dot structures, which we did for this one too, we end up with this type of a structure. I'm just going to draw lines here. And then we had a lone pair on the central atom, okay? Now you can see that the sulfur-oxygen bond is a polar bond, okay? And the first one goes from left to right in the positive direction, if you will. But the next one, the other one, is going from right to left, but it's not in the same direction. It's going, yes, in the negative, but it's going sort of like in the southwest direction, if you will. Whereas the other one, the way I drew it, is going in the east direction. So they're not canceling each other out. They're going in totally different directions. The result is that we have two polar bonds that do not cancel each other out. And that implies that we have a polar molecule. And since we have a polar molecule and to assign a force to it is definitely not London dispersion forces. It's not that because it's polar. It is not the ion dipole because we have no ion here, just sulfur dioxide. Okay. And it's not the hydrogen bridging force. Why? Because there's no hydrogen, again, sulfur dioxide. So the only other force left to assign to this is the dipole-dipole force. And that is the force for sulfur dioxide. Okay. And that's how we went through assigning that force to it. We figure out the polarity of the molecule. And then from once we know the polarity, we can assign a particular force. Now, why do we want to do this? Because we're going to be able to take two different molecules and based on their force that they've been assigned to do a relative comparison with respect to some physical properties like boiling point. We will be able to predict of two different molecules, which one will have a higher boiling point or a lower boiling point, depending on how you ask the question. Okay, so to rehash here, once you have polar bonds, it does not automatically assume that you're going to have a polar molecule. If the polar bonds cancel each other out, then you end up in a nonpolar molecule and automatically you go to London dispersion forces. If they do not cancel out, that is the polar bonds, then you have a polar molecule, and now you have to determine, do I use a London a dipole force or a hydrogen bridging force. Okay. All right. That's basically let's go back to where we were there. So all right, with that information, we are able now, hopefully, to look at the given any molecule, assign to it its polarity, and then from that, assign to it the strongest intermolecular force for that particular molecule. Okay. We have talked about carbon dioxide. We determined that carbon dioxide is nonpolar. Excuse Give me two seconds. Oh, this is crazy allergies. Still kicking me. All right, so we had carbon dioxide, of which we just talked about. Carbon dioxide is nonpolar, okay, based on the structure, the geometry. We determined that it's a nonpolar species, okay. That being the case, the only force that can be assigned to it is the London dispersion force. Now, the next one, you may not be familiar with, but if we do the Lewis dot structure for PF3, we count up all the valence electrons, and phosphorus is the central atom, we can, to refresh your memory, come up with a formula, structure, which will be as follows. And then we end up with a lone pair on the central atom. And so the general formula here would be A, B, 3E. E represents a lone pair in the central atom. When we were doing this, the Lewis dot structure chapter, I mentioned this, put this in long-term memory. When you do the Lewis dot structure and you end up with a lone pair at the minimum on the central atom, you will always, 100% of the time, always have a polar molecule. Okay. Now, here, and that's because what happens, if you recall, when you have a lone pair in the central atom, those two electrons in that orbital will take up a lot of space. They're going to repel each other. The result is that this bond angle gets shrunk from its reference point that, if you recall, was 109.5 degrees. That was like the benchmark of most molecules with four atoms bonded to a central atom. That's the maximum distribution, maximum bond angle one can have with four atoms around the central atom. Well, once you have lone pair, that squishes that bond angle, and that results in three polar bonds that will not cancel out. And that being the case, you automatically have a polar species. Okay. Now the question is, which force to assign? Well, obviously we're not going to assign to it any London dispersion forces like we did before. I'm just going through the process of elimination. And it's not going to be the ion dipole force because there's no mention of ions, it's just P of 3 itself. And so all we got left is the dipole force and the hydrogen bridging force. Okay. Well, here again, no hydrogen bridging force because we don't have hydrogen involved with the molecule. So the only force left to assign to it would be the dipole force. Okay. All right. Hydrogen fluoride. Well, here we have, it's a polar molecule. No questions asked here because automatically, I think I had used the general scenario with respect to a bond, where I said that A bonded to A versus A bonded to B. Okay, and I used letters to give you a general example. And I said, when A and A represents that the atoms are the same. Okay, and the fact that they're the same means that they have the same amount of electronegativity, so there's an equal sharing here. So whenever the two atoms are the same, you always have a nonpolar bond. Included in there was the example of carbon-hydrogen, because the electronegativity between carbon and hydrogen is basically the same. It is treated as a nonpolar bond. Okay. Now, with respect to an AB scenario, we got two different atoms here. Doesn't make a difference what they are at this point, but automatically the fact that you got two different atoms, you have a polar molecule. Okay, polar molecule. So HF is a polar molecule automatically. It is the AB example. All right, so once we know that, then we assign the bond. Well, obviously, again, we're not assigning LDF to it because it is polar, and that's not the case. And we're not assigning the ion dipole force because there's no mention here about ions, like this example that we're going to talk about. And then we have what's left is the dipole force or the hydrogen bridging force. Okay, well, that's supposed to be hydrogen H. Here's the interesting thing here. Hydrogen bridging force. We do have hydrogen, which happens to be bonded to fluoride, which is one of the three atoms that is required for it to be assigned hydrogen bridging force. Is hydrogen bonded to either nitrogen, oxygen, or fluoride. And in this case, it is fluoride, so its force is the hydrogen bridging force. Okay. All right, the next example is, again, you may not know what it is, but I hope you can observe here that all you have is carbon and hydrogen. That being the case, that means that all bonds there are nonpolar because carbon-hydrogen bonds are treated as nonpolar bonds. Okay, so it means that methane, FYI, this is methane, is a nonpolar molecule because it has all nonpolar bonds. Okay, then the only force assigned to that would be the London, and that's it. So notice that the first four examples all dealt with covalent compounds. The next example, you have an ionic compound, which happens to be an aqueous solution. The fact that it's ionic compound tells you, okay, we're dealing with very polar water, just water. So the only force that you can assign to it is the ion dipole force, okay? And here's the thing that to remember. The ion dipole force only pertains to ionic compounds in some polar solvent, which is most of the time kind of be almost 100% of the time an aqueous system. Okay, so you will never see a situation where you have all these covalent compounds being assigned the ion dipole. Okay. All right. Now, with now the assignment that has been made, the weakest interactions here are those with the London forces. Okay. The strongest is those with the hydrogen bridging, and then the dipole is somewhere in the middle. Now, when we start doing comparison, we're only dealing and comparing covalent compounds, only covalent compounds. We're not going to be comparing with ionic compounds. So what I can state at this point in time, and we're going to talk about this in more detail with respect to boiling point. The boiling point is that temperature that a liquid goes from the solid to the gas phase. That is the temperature that it boils. Okay. Now, because the strength of the intermolecular forces involved here, that boiling point is that molecule has would be determined by the force. So those that have London dispersion forces would have the lowest boiling point. Okay, and why? Because those molecules that have the lowest, the weakest IMF, it doesn't take much energy to break up that interaction, the IMF. Remember, IMF is the force between molecules. And if that force is strong, it's going to take energy to break it apart. When it's in the liquid, they're attracted to each other and they're being, kind of hanging around in the liquid phase. All right. And as I put energy into the system, it's causing these molecules to move around even greater apart, and such that if I have enough energy, I can cause these molecules to get away from each other or whatever distance they're at to further apart to go into the gas phase. Okay. So the hydrogen bridging forces, it's a little bit stronger. Okay. So I would anticipate that the boiling point of HF, hydrogen fluoride, would be much, much greater than the boiling points of the other molecules, simply because its intermolecular force is much stronger. And I'm going to require more energy to break up the molecules of HF than it would take for the other molecules. Okay. And that's what we're going to start talking about, these different physical properties and how we can do a prediction. And we won't be able to predict absolute value. If I give you absolute values, it's simply because I know what the number is, but we can do comparison, A versus B, which one's going to boil higher, or the question would be which one can boil lower, okay? And to answer that, we have to first assign a polarity to the molecule. Once that's been done, we assign a IMF to that molecule. All right. We're going to bypass Coulomb's law. There's not much to say about this. There's an equation. I meant to block out these slides, but bypass Coulomb's law. In essence, what that is a measure of attraction of and strength of charges have to with each other. Excuse me. Sorry about that. Okay, so let's move on. All right, so what we have here are some questions. Now, what is being asked is, are we dealing, what is being dealt here is are we talking about a bond, or are we talking about an IMF, an intermolecular force? Okay. And that's what we need to discern from the question. Is the question asking us, are we talking about the bond? Remember, that is intramolecular force. Are we looking within the bond to determine how are the atoms held together? Or are we talking about interaction? How are these molecules interacting with other molecules of itself? Okay. All right. So key is to read the question carefully. Here it says, what holds the atoms together in one ammonia molecule? The fact that it's telling you one molecule, we are talking about intramolecular forces. What is holding the atoms, the hydrogens and the nitrogens together? And that would be a bond. Well, once we discern that, we just need to know what type of bond. Okay. So what we have here is a nitrogen-hydrogen, which is a covalent bond, okay? And more specifically, it is a polar covalent bond, okay? Nothing was said about IMF. If the question was about other molecules, then we would have to assign to it a particular IMF. But here we're talking within one ammonia molecule, okay? Next one. What is holding the sodium ions in water? Well, here we have sodium ion dissolved in water. And there is only one force that deals. We're not talking about the question doesn't ask what are the sodium ions themselves, how they attracted to themselves. They're talking about the ions in water. So that is a force, right? IMF, specifically the ion dipole force, okay? All right. Next question says, what is holding three HCl molecules together? The fact that we're talking about more than one, three, and we're talking about HCl, the molecules together, here definitely we're talking about it. They're asking about IMF, okay? What is holding these molecules together? So we got, if it does help, draw them out. We got an HCl. What is attracting these together? Three of them. What's going on here is the question. What kind of force is keeping them together? Well, to do that, we need to determine if it's a polar molecule. Yes, it's polar. Okay, HCl is polar. All right, so that eliminates London dispersion forces because it's polar. Also eliminates the ion dipole force because there's no mention here about ionic compounds. So what we got left is dipole force and hydrogen bridging force, okay? So you might think, okay, hydrogen bridging because I got hydrogen. But remember, hydrogen bridging force only pertains to those hydrogens that are bonded to nitrogen, oxygen, and fluoride. So that eliminates hydrogen bridging force. So the only force involved here is the dipole force. Okay. See how we went about and just went down the list of things and eliminated choices. All right, what is holding? Clear my. What is holding the ions together in salt or sodium chloride? All right, so first point, no mention of water. So we're not talking about a solution, an aqueous solution. It's just talking about what is holding the ions together in sodium chloride. All right. So we have sodium chloride, metal, non-metal. So obviously it is not a covalent bond. So the only other choice is an ionic bond. Okay. Ionic bonds are holding the sodium chlorides together. Next question. What is holding four H2O molecules together? Like, again, we're talking about water molecules relative to other water molecules, right? So we know that water, to put this in long-term memory, is polar. No questions asked. Water is the most polar solvent that there is. Okay, so it is polar. So that eliminates London dispersion forces and ion dipole. There's no mention here about ions, ionic compounds, just simply water molecules. We can also eliminate dipole-dipole force. Why? Because we're talking about hydrogen bonded to oxygen, which means that the only force we can assign to, it's not the only force, the best force to assign water molecules would be hydrogen bridging force. Okay, hydrogen bridging force. I think the question is about this hydrogen bridging force. The thing to remember is this: we have hydrogen bonded to nitrogen, hydrogen bonded to oxygen, hydrogen bonded to fluoride. Okay, those are the three types of bonds, and now they could be in part of any other molecule, you know. But HF is, there's only one HF. That's it. One hydrogen fluoride compound. When it's bonded, hydrogen bonded to nitrogen and oxygen, you have a multiple of different types of compounds. Doesn't make a difference what this multiple is, as long as there is a nitrogen bonded to hydrogen or oxygen bonded to hydrogen. Okay, and that assigns that you can assign that to hydrogen bridging force. All right, what holds nitrogen gas molecules to each other? And so the way they worded in the previous one, they said 4 molecules, 3 molecules. Here, they're just giving you a carte blanche number. You know, what are these gas molecules? How they are being held together to each other? Okay, so definitely that's an IMF. So what do we know about nitrogen gas? It is diatomic. Being diatomic, automatically it is a nonpolar molecule. Being nonpolar, the only force that they have is the London dispersion forces, which again are temporary and the weakest of the total of the 3 forces. Now, next one says, what is holding the oxygens together in an oxygen gas molecule? So we're talking about just the molecule itself. What type of bond we're dealing with? It's not ionic, so it's covalent. And more specifically, since the oxygen gas is diatomic, which is nonpolar, it is a nonpolar covalent bond that is holding the oxygen atoms together in one molecule of oxygen gas. And then finally, it says, what is holding 2 ammonia molecules together? So you can see here we're not talking about the bonds themselves, we're talking about the molecules and how they're being held together with each other. All right, so we're talking about IMF. Ammonia is very polar, okay? And to refresh your memory, if you don't recall, we did this in Lewis-Dot structures, so you might as well commit that to memory. So ammonia had this particular Lewis-Dot structure, and guess what? We got a lone pair in the central atom, which automatically tells you it is polar. Okay. Once we know that, we got hydrogen involved, which happens to be bonded to nitrogen. All right, which tells us this has to be hydrogen bridging force, based on the question we're talking about. What are 2 molecules of ammonia? What is holding them together? You know, something like that. What is holding them together? So in this particular case, it is the hydrogen bridging force. Okay. The takeaway from these type of questions is as follows. Read the question carefully. Is the question asking what is happening within the molecule or what is happening with other molecules? Okay, and if you don't read the question carefully, you might instead of being given the force, you might be given the bond. Okay, and vice versa. All right. Any questions about these type of questions? All right, well, it's a flow chart, kind of a crazy looking flow chart. The flow chart instrument wasn't working. This is kind of really out of place here, but I'll explain that in a second. So first of all, we first define whether it's a covalent bond, okay? If it's a covalent bond, then automatic next step is to determine whether it's polar or non-polar. If it's non-polar, then no questions asked. The only IMF assigned to it is London forces. If it's polar molecule, okay, then you have either dipole or hydrogen bridging. Well, hydrogen bridging, again, is only those scenarios where you have hydrogen bonded to oxygen, nitrogen, or fluoride. Only in those examples that then you have hydrogen bridging. Otherwise, if it's not that scenario, then whatever's left is dipole. Okay. Now, this really should not be here. I'll get this corrected. But here, what we're working with is ionic. If it's ionic, then if we're talking about IMF, then it's going to be in some aqueous system. Okay. And then if that's the case, then it is the ion dipole force. All right. Which brings us to the physical properties. I introduced boiling point here, but we're going to introduce 3 other physical properties of compounds, of molecules, and how IMF interacts or affects these physical properties. All right, so for example, we have what are called vapor pressure, okay? Vapor pressure deals with actually pressure of vapor in a closed container. I have an example here in a second. Next slide. Next factor, next physical property is called boiling point. That is the temperature that a compound goes from liquid to gas phase. Then we have surface tension, and then we have what is called viscosity. Viscosity is a measure of the resistance to flow. And if something is highly viscous, it's going to flow less, something thick. For example, honey is very thick, has high viscosity compared to water, which is not as thick and has low viscosity. All of these physical properties are affected by the IMF. And if we look at how strong this IMF is, we can, think of it I look at it in these terms. The way I think of it with respect to the 3 forces, and when we compare this, when we're talking about IMF, we're not going to be looking at the ion dipole, simply London dispersion, dipole, and hydrogen bridging, those 3, okay? And the way I kind of look at these to help me out is when I look at London dispersion forces, those are the weakest. I think of them as like refrigerator magnets. They're very weak. Refrigerator magnets, you put them on the refrigerator and you want to take them off, it doesn't take much energy to yank them off. They're fairly, the strength of that magnet is not very strong, okay? Now, on the other end, the hydrogen bridging force, I think of those back in the day when I was doing research, I used to work with very super magnets, very strong. It took a lot of force to pull them apart, okay? So these are like extremely strong magnets. So we got a weak and very strong. And then the dipole force, somewhere in the mid region. It's not as strong as the HBF, but it's much stronger than London dispersion forces. And if I think of those in terms of magnets, all right, so I got two refrigerator magnets interacting with each other, they're attracted to each other, but it doesn't take much energy to pull them apart, right? Then in the other end of the spectrum, I guess something has been assigned to HBF that has, to me, in my mind, associated with it, the strong magnets. Man, it requires a lot of energy to get those things yanked apart and separate. Because remember, when we go through the physical changes of solid, liquid to gas, what we're talking about is how well these forces are holding on to each other. And when we put energy into the system, energy like heat, we cause these molecules to start moving and start separating. Now, if that energy that holds them together, attracts them together, is strong, it's going to require a high amount of energy to get them broken apart. Okay, high amount of energy. Think about this: water boils. I'm going to use this as an example. Water, H2O, has a boiling point of about. Oh, something happened to my. Of about 100 degrees Celsius. That's pretty hot. That's about 212 Fahrenheit. So 100 degrees Celsius is the water boiling. But water boils. So it takes a lot of energy. I think of those in terms of when I assign a force to it, I assign, London hydrogen bridging force to water. And I think of it in terms of super hard, strong magnets. And it takes 100 degrees of energy to get them separated so I can push them into the gas phase. Whereas if you look at, fingernail polish remover, which is normally acetone, I'm sure you opened up a bottle of fingernail polish remover and it's very volatile. The odor comes out very quickly, you smell it. Its force to keep the molecules together is much weaker. Room temperature is enough energy in it to cause these molecules to go into the vapor phase. Okay, so that I think of it in terms of the refrigerator magnets, if you will, and it doesn't take much energy to pull them apart out of the liquid phase and send them off into the gas phase. Okay, and all this pertains to all. I just mentioned boiling point, but this all affects these different parameters, these different physical properties. Okay, so vapor pressure is one way to look at it. Is if we have a closed container, I don't have a soda pop container, but if I have a container, and I got it capped, and I got it liquid here, right? So here's my soda pop. Well, I know up here I have gas molecules up in the dead space, if you will, with the air. This is the liquid, but there's gas molecules up in there. And if I were to put a meter here on the side of the airspace, I can actually measure a pressure because there's gas molecules in there. Okay, just like you can measure the pressure of your tire, there's gas molecules, air molecules in your tire to give you air pressure. All right, so that is what we're talking about when we talk about the vapor pressure. So, how many molecules come out of the liquid and go into the gas phase? The more molecules that go into the gas phase, the higher the vapor pressure. Okay, think about that for a second. The more molecules that go into the gas phase in the closed container, the higher the vapor pressure. That means that if in the liquid phase, if they are held on to each other loosely, then more gas molecules go into the gas phase and the vapor pressure is higher. That implies that the IMF in the liquid phase is not very high. So the converse is true. If the IMF is very strong and the molecules are being held onto each other tightly, and require more energy to get them separate, then the vapor pressure is not as high. Okay. It's all function of the IMF of the material in the gas liquid phase. So for vapor pressure, if we have a strong IMF, we would expect a lower vapor pressure, like I just explained. So one way to look at it is by these diagrams. Okay. Look at a diagram. A lot of gas molecules are in the gas phase. Okay, there's a lot of molecules in the gas phase compared to B. Okay, so that infers that the force here to separate these molecules is much lower. The IMF is lower in A than in B, because B, it would be higher IMF because it takes more energy to get these guys to be separated that are in the liquid phase and push them up into the vapor phase. Okay. So the question says, which has a weaker IMF? But that would be A, because they have a higher vapor pressure. And it's weaker IMF, meaning that more molecules are being allowed to go into the gas phase because it doesn't take much energy to separate. It's the refrigerator magnitude, if you will. Okay. And so therefore A would have the higher vapor pressure compared to B. B, they're just the stronger magnets, if you will. You're taking more energy to get them separated to push them up into the gas phase. So we would anticipate a lower vapor pressure and a stronger IMF for B as compared to A. Now we haven't assigned specifics, but if I wanted to assign, be specific, I could say it suggests that for A, maybe there's London dispersion forces. And for B, maybe there's hydrogen bridging forces involved here. Okay. All right. Oh, come on. There we go. All right. With respect to boiling point, again, you will have a higher boiling point if you have a stronger IMF. Again, going back to the example we were doing earlier, the diagrams, it would take more energy to break up B than it would do for A. So I would anticipate a higher boiling point for for B than for A. Okay, because I need more energy to get more molecules into the gas phase. That would also pertain to melting point. I know we did mention this should really be another physical property, and that's melting point. But the same process, be it melting point or boiling point, is this: you have some solids that would their melting point would be higher, again because their intermolecular force is much stronger. It takes more energy to cause a solid to go into the liquid. And that's what melting point is, transversing from a solid to the liquid. And the temperature that it does that transversing is dependent on the IMF force that it has, okay, which is dependent on the polarity of the molecule, okay, polarity of the molecule. Now, surface tension is another one. Surface tension is a measure of how well molecules hold on to each other. If a molecules hold on to each other very well and you put a drop of liquid on the surface, if they're holding on very tightly, they beat up, okay? So on the left, you can see that it has A has a higher IMF, okay? Because the molecules are hold on to each other much tighter than B. And so A tends to bead up, whereas B, with the lower IMF, its liquid tends to kind of flatten out on the surface, okay? And then we have viscosity. Viscosity is a measure of the resistance of a liquid to flow. So oil, and most oils, they flow slowly because they are highly viscous, which means, again, based on their IMF, the molecules are holding on to each other much, much tighter. Whereas something like an alcohol, for example, or water, very rapid, okay? Because its IMF is not as strong as in the case of oil. We can, stronger IMF, we have higher viscosity. So if we had a cup of honey and a cup of water, if we take those two cups and empty them, obviously the water is going to win that race as far as emptying that cup. Oil is going to take a little extra time to completely exit the cup because it's more viscous. Now, to put it in perspective, how can I make that oil flow much quicker? Any suggestions? How can I make honey, not the oil, honey? How can I make honey flow a little bit quicker? What can I do to it? Any suggestions? What about heating it? What if I heat up the honey? Wouldn't it flow? Right? It would flow much easier. It's like taking a block of chocolate. You got solid chocolate. It doesn't flow very well. But if I heat it up, I'm melting it and I'm increasing its rate of its flowness and decreasing its viscosity. Okay, so in this scenario, we're going to do some compare and contrast. All right. And so to do that, first we need to know the formula for ammonia, which hopefully you got this memorized by now because we use ammonia quite a bit. All right, so we have ammonia, its formula is NH3. And fluorine, it should state fluorine is F2, diatomic. All right, so with that being said, we know that ammonia is polar, okay? And we know that fluorine being diatomic is nonpolar. With that information, then we can go on and assign a specific force, okay? Because we have nitrogen bonded to hydrogen. We can assign to it hydrogen bridging force. And fluorine being diatomic is nonpolar, so the only force it has is London force. So once we assign the force, now given the strength of the force, we can start doing a compare and contrast because the London forces are the weakest compared to hydrogen bridging. Hydrogen bridging of the three is the strongest. Okay, so those molecules of ammonia are held down to each other with a greater force than those molecules of fluorine relative to each other. Okay, so and with that, we are able to answer some questions about this. Here, number one says, which is the stronger IMF? Well, I already answered that. Hydrogen bridging is the stronger IMF, so ammonia has the stronger IMF, okay? Which has the lower boiling point? Well, the one with the weakest IMF would have the lowest boiling point, so that would be fluorine, okay? Because though having London forces, those forces are not very strong at all. So they would readily go into the vapor phase with not as much energy needed as compared to ammonia, okay? All right, which is polar? Well, that was answered in the beginning to be able to assign a IMF. And ammonia is the polar species here. Okay, which has a higher vapor pressure. higher vapor pressure. Well, that would be the one with the lower IMF, and that would be fluorine. Okay? Because if there'll be more fluorine in the gas phase than there would be for ammonia. So if we had a closed container of both of these compounds, we would see that fluorine would definitely have the higher vapor pressure. Okay, and which is the least viscous, meaning if both are in the liquid phase, which one would flow easier? Okay, and again, the one with the weaker force will allow for a greater flow rate, if you have a greater flow, because again, the molecules within fluorine are being held on with less energy than for ammonia. And then the one with the surface tension, obviously the one with the higher IMF, which in this case is ammonia. Okay. And I think there's one more. No, one more. Now it's 6. So to rehash here, one could come across these type of questions. They could be reversed. Instead of saying which has the stronger IMF, it could be which has the weaker IMF. Number 2 could read which has the higher boiling point, vice versa. Okay. So but in order to answer the question, again, we're doing a compare and contrast between 2 different molecules, and we're not doing absolute values. We're doing which one is higher or lower. We first have to write the formula, know the formula, and from that be able to assign to it a particular IMF, and then determine from the IMF that we assigned which is weaker, which is stronger. Now, if, for example, both of them turn out to have the same IMF, then the question is which one is bigger, okay? Because within the forces, those compounds that have strong, which one has a stronger IMF is dependent on the size, okay? So if the compound is bigger and they have the same force, they will have more of that force simply because of their size. All right, to put it on, summarize everything it says here. As the IMF increases, the viscosity will increase. Increase the IMF, increase the force. It requires more energy. The molecules hold on to each other much with a tighter force, if you will. Therefore, the viscosity increases, the boiling point increases, and the surface tension increases. Okay, because again, the molecules are being held on to each other much tighter than the other forces, which means that the vapor pressure in the closed container of that compound will be smaller, because the majority of the material would be in the liquid phase and not readily be allowed to go on into the gas phase until we put energy into the system. Okay. All right, a couple of words about water, not much to say. We had talked about this. I've spoken about this before. Doing Lewis dot structure, water is kind of unique in itself. It's 2 bonding electron pairs. We have 2 non-bonding electron pairs. Its geometry is called the bent molecular geometry, with that bond angle being much, much less than 109.5, which was our standard, our reference point bond angle. Water is very polar and will dissolve most anything. All ionic compounds do dissolve in water. Yes, based on the solubility rules, there's degrees of solubility. If it's defined as soluble, yes, 100% of it goes in solution. If it's defined as insoluble, majority stays out of solution, but there still is some ions in solution. Okay, so water is very polar. Very strong hydrogen bridging force in the molecule, and therefore that's why the boiling point of water is so high, 100 degrees Celsius. Has a high, very polar, high IMF, very low vapor pressure, okay, because of the high IMF. Boiling point's at 100 degrees and melting point temperature that solid goes to liquid is at 0 degrees. High surface tension. And interesting aspect about water, when it goes into the solid phase, it actually expands when it goes from liquid to solid for a given equal amount of volume. And that volume, when it freezes, it actually expands and therefore results in a density, which is much less than the water itself, which means the water in the solid, because of the increase of density, will float. Not increase in density, decrease in density, which is due to the increase of the volume. Okay, for a given same equal amount of volume. Because density, if you recall, is a ratio of mass over volume. So if I have 1 gram of water, I have 1 milliliter of water. Okay, if I take that same 1 gram and I freeze it, it no longer is 1 milliliter, it could be like 1.1. So that ratio 1 divided by 1 for liquid is 1 gram per milliliter. But now the ratio 1 divided by 1.1, you got a number is less than 1, about 0.9. So the density is much less than 1, meaning that in water, solid ice will float. It's crystalline structure here to the left, very, very ordered, structured. Also, you can see you got like a 6-membered ring, hexagon shape. That's very common for, that's a common geometric shape in nature, 6-membered ring. It's supposed to be very strong. Anyway, there's a microscope picture of a snowflake there on the right-hand side. Okay, which brings us to heating curves, which is related to the IMF of compounds. And what we have here is a typical heating curve. Let me draw some stuff out here. We have on the x-axis, y-axis temperature, okay? And then we're adding an X amount of heat. And so we add an X amount of heat, we take a measurement, we end up with this particular graph. So here on the far left is solid, a compound, whatever it is solid. As we put temperature, put heat into the system, obviously the temperature goes up. But then something surprisingly happens. We reach a plateau, okay? And even as we give it more heat, more energy, you still maintain a plateau at some temperature. Okay. Then all of a sudden we get a big rise, we start another rise in temperature. This is the area of the liquid. But as we did the first time, we hit a second plateau, where again, no matter how much heat we put into the system, it still remains a plateau until such point that the temperature increases again. And this is what we call the gas phase, okay? What's interesting that we're going to talk about are these 2 plateaus. That plateau represents the boiling point of that particular liquid, okay? And how it's related to the IMF. All right, so we've got the same heating curve again, but a little more information on it. In this case, we're going to use water as the example. All right, water, like I stated, boils at 100 degrees Celsius, and it melts at 0 degrees Celsius. So we start with a block of ice, chunk of ice, and we start putting energy into it. So you take your ice cube of ice and we start heating. Well, obviously a temperature increases. In that area where you get a temperature increase, your ice still remains ice, it's solid. When the first plateau is reached, in this case for water, it's 0 degrees. At this point, all of the solid is being converted to liquid. Okay, solid is being converted to liquid. So the energy you put into the system here is breaking up that intermolecular force of those molecules. And so where you may have had starting off with a very ordered solid, okay, and as you put energy into that system in that first plateau, now it's, not as ordered. I'm trying to make the net as ordered, so a little bit of separation, kind of, if you get the gist of it. So all of the energy you're putting into the system is being used to break up the IMF. Okay, break the IMF interaction to go from solid to liquid here. Actually, it's a combination of solid and liquid. Now, at such point that all of the solid has been eventually converted to liquid, we get an increase in temperature. And during the increase, it's all totally liquid until such point. And it continues to absorb that energy. You see, you're still heating it until you hit that first plateau, second plateau. At that point, all of the liquid now is being converted to gas. So here, the molecules are now really getting separated. Okay, all that energy is being converted. And so we have a second plateau where it's at 100 degrees for water. And it's going to vary depending on the molecule or the compound that you have. When all of the liquid has been converted to gas, then we get another increase in temperature, and that can go up to whatever temperature you can bring it up to, but it's all in the gas phase now. So we have two plateaus. The first plateau is where the solid is being converted to liquid, and then the second plateau is where the liquid is being converted to gas. And there's no increase in temperature. So, one main takeaway from this is for home use is that, as you're boiling a pot of water and it starts to boil, you can turn that heat down. You're not going to increase that temperature any higher once that water is boiling, because all of that energy you put into the system is going to be used to break up the IMF of the water molecules. It is only until all that liquid in that pot has been converted to vapor that the temperature will increase. In that case, you won't have any water to boil anything, okay? So anyway, save you some money, save you some energy. Once you get it boiling, you can kick the heat back a little bit, keep it stable, and don't worry about putting more heat into it because you're not going to make that thing boil any quicker or any higher in temperature. Okay. You can try this at home. As you boil water, I'm sure all of us have thermometers at home, kitchen thermometers. Stick that thermometer in that water. Let it sit there. You'll see that temperature just be constant throughout. Turn up the heat a little bit. Still going to remain. If you have a thermometer, it'll probably be 212 Fahrenheit. Obviously, you may not have one centigrade, but yeah, it's all, that temperature remains the same. Okay, so during this time period, the temperature remains constant at the plateau. All of the energy is used to break up the IMF. What's important here is not breaking up any bonds, okay? The amount of energy necessary to break a bond is extremely much greater than the energy that we've been talking about. All we're doing is breaking up the IMF, all right? And you're just dealing with intermolecular forces, not the bonds. All right, well, I want to congratulate you. You have just finished chapter 14. Okay, any questions about that chapter? Yeah, just save it. Tell you what. Our next chapter we're going to talk about is coffee. No. Solutions, very short. And what we'll do is tell you what, why don't we, let's stop the share for a moment. let's take a quick break. Let's do 15 minutes because this one's not going to take the full time. Okay. Okay. Let us continue. Finish up this last chapter. And let's talk about solutions. All right. All right. So what is a solution? Well, by definition, simply put, a solution is a solute dissolved in a solvent. Okay. Now, normally the solute is whatever chemical or material that is present in the smaller amount, where the solvent is whatever is present in the larger amount. Now, normally here in the lab in chemistry, water is the most common solvent, but it doesn't have to be water. It could be even an oil. And it doesn't necessarily have to be a liquid. It could be other things too. We'll talk more about that in a second. Now we're going to concentration. Concentration is simply, we're going to have some means to calculate concentration, but it's basically the amount of solute in the solvent. If you have something that's concentrated, you have a lot of solute. Okay, so denoted by, for example, these colored drinks here, you can see how on the far right, very concentrated, just more solute than the one on the far left. It's just a weak solution or diluted, okay? Now, as I stated, it's not always a solution, it's not always a liquid or solvent of some sort. It could be a solid, combination of solid in a solid or solid in a liquid or liquids and gases and so forth. Let me give you some examples. For example, you can have a solution of a gas in a liquid, like a carbonated soda, your soft drink, for example. You have carbon dioxide that's been bubbled through the liquid, okay? Or you can have liquid in the liquid, like a mixed drink, vodka and tonic or vodka and water, okay? That's a solution. You can have a solid in a liquid. So you take sodium chloride, put it in some water, then you have a salt solution. And so, or it could be gas in a gas. So the air around us is a mixture of gases. So, so most of the time it's either gas, liquid, or solid in a liquid, or it could be gas in the liquid or gas in a gas. Okay. But you can also have solid in the solid. A lot of metal alloys are basically technically a solution. For example, steel. Steel is a mixture of iron and some carbon of different concentrations. That additional carbon gives steel strength and different properties. Other examples would be brass. Brass is a mixture of zinc and copper. Okay. And copper, for example, we can put additives in it. I've worked with copper less for many years, but generally copper is very soft and pliable material, but you can fix copper such that it's just as strong as steel by adding different additives to that. Okay, so those are different examples of solutions. Now, the golden rule, if you will, like dissolves like. We talk about polarity and what polar molecules will dissolve in polar solvents, okay? So polar solutes dissolve in polar solvents because of their polarity. The counter to that is nonpolar solutes will dissolve in nonpolar solvents. Now, it's not always a strict black and white. There are examples of polar components, compounds that can dissolve to a certain extent in nonpolar solvents and vice versa. But as a general rule, that this applies. Like dissolves like. Like we know that nonpolar and polar do not mix. Case in point, an oil spill. You have oil, which is basically hydrocarbons, which are nonpolar. And then you got the ocean here in this example, which is mostly water, obviously, which is very polar. Well, when we deal with liquids, we talk about, normally we talk about soluble or insoluble, but that's the case when we're dealing with solids and liquids. But when we're dealing with liquids interacting with each other, they're either going to be miscible or immiscible. So when two liquids mix, because of their likeness and polarity, they are classified as being miscible. When they don't mix, like the case in point, the picture to the left, oil and water, they are classified as being immiscible. Okay. So if it's a solid that dissolves in whatever solvent, then it's soluble. If it's not, it's classified as insoluble. Remember the solubility rules. These are for ionic compounds or ionic solutes dissolved in a water solvent. Okay. They definitely wouldn't work very well with respect to non-water, non-aqueous systems. All right, so we have a table here, and the question is, will these solutes dissolve in the solvent? So on the top row, we have the solute, hydrochloric acid, HCl, iodine, PF3, and CH4, okay? And then we have the solvents on the left column, first column, NH3, which is ammonia. Then we have a hydrocarbon, okay? And then we have bromine, okay? Now the question is, would these solutes dissolve in a large quantity of the solvent? Well, to answer that, we first have to determine the polarity of the molecule. Okay? So we know that based what we talked about, ammonia is very polar molecule. C12H26, nothing but carbon and hydrogen, which means all nonpolar bonds, which tells you it is a nonpolar species, okay? And then Br2, which is a diatomic element, again, would be nonpolar, as all diatomics are nonpolar. With respect to the solute, hydrochloric HCl, we talked at length about this, definitely polar, okay? Iodine, which is another diatomic, okay, also nonpolar, being diatomic. PCl3, phosphorus trichloride. Well, to determine whether that is polar or not, what you have to do is literally you have to draw the Lewis dot structure for that. And it's going to be very similar to ammonia. In fact, if you look at nitrogen and phosphorus on they belong to the same group. And so what you can draw from that is that you will end up with the same, similar, let me change this for a second. You end up with a similar type of structure where you have 3 chlorides to the phosphorus, okay? Obviously, you're going to have a lot more valence electrons than you would for ammonia, but the structure will be the same. A, B, 3E, the same for as in ammonia. Except ammonia has hydrogens instead of chlorides. But they both will end up with lone pair on the central atom. That being the case, as I stated, anything with any molecule with lone pairs on the central atom would be classified as polar. All right. And then finally, the last one, we have CH4, which is nothing but carbon hydrogen, meaning it's a hydrocarbon, which tells you it is a nonpolar compound because all the bonds are nonpolar, nonpolar covalent bonds. All right, once we define the polarity of both the solute and the solvent, then remembering like dissolves like, we can determine if the solutes will dissolve in the solid. So the first set would be yes, we have a polar HCl, it will dissolve in ammonia. Okay. No for the second iodine because it is nonpolar. You will not get it to dissolve very well in ammonia. Yes for the PSCl3 because they're both polar, and no for the methane. Okay. Next one, the solvent, the hydrocarbon solvent, no for the polar HCl, yes for the nonpolar iodine, no for PCl3 because of the difference in polarity, and yes for methane. And then no for bromine as a solvent for HCl, yes for iodine. Iodine will dissolve in a larger solvent or quantity of bromine. No for PCl3, okay, because a difference in polarity, and yes for methane. So you've given a table of different solvents and solvents and solutes to determine whether they will dissolve in each other. You have to first determine the polarity of the molecule of both the solute and the solvent. Once you determine that, keeping in mind the golden rule, if you will, like dissolves like. Nonpolar will dissolve in nonpolar, polar will dissolve with polar. With that information, then you're able to answer and predict solubility or not. Okay. In this case, they're asking you, okay, use the terms miscible, immiscible, soluble, insoluble, and recall that miscible and immiscible are used when we're dealing with solute liquid and solvent liquid in both solute and solvent. And soluble, insoluble, we're dealing with solid and solvent. Okay. So in the first case, it is miscible because again, like dissolves like, polar solvent, polar liquid. Immiscible because we have a nonpolar differences in polarity. Immiscible again for differences in polarity, but miscible in the second case. Again, we're using the term miscible, immiscible because we're dealing with liquids. Okay. The solid would be soluble, this polar solvent, solid, I should say, because it would be soluble in a polar solvent, but would be insoluble in a nonpolar solvent. If it's a nonpolar solid, be insoluble for a polar solvent and soluble for a nonpolar solvent. Ionic compound, it depends. It depends on the solubility rules. Okay. The previous examples, we were dealing with covalent compounds with respect to solvent, solute. Here we're dealing with ionic compounds, so we have to check the solubility rules and see if it will be soluble in a polar solvent, specifically water. But no questions about it, you will not find any ionic compound, to the best of my knowledge, that demonstrates solubility or any type of solubility in the nonpolar solvent. It could be partial, but for Chem 130, we're basically going to be insoluble. Okay. Simply because, and let me qualify that comment, because simply there are ionic compounds that have with it, associated with it, a nonpolar component. A good example would be soap. Soap is basically a long hydrocarbon chain, nonpolar tail, if you will, with a polar head. We call it a head, but there's a group of on the one end of it is very polar, and the other end is nonpolar. So it has both polarity and non-polarity characteristics. But because of that, it can act as a detergent and remove oils and greases from clothes. Anyway, they just say for Chem 130, an ionic compound will be considered as insoluble in a non-polar solvent. The dissolving process, we kind of touched on it when we talked about the ion dipole force. You basically have the sodium ion, in this case, solvated completely around with the water molecule. Okay. And there's not much more to say about that. Okay. All right, let's talk about concentration. We have two types of concentration that we're going to work with. One is the mass percent, which is a weight percent. Sometimes you have out there in the market, you may have a weight volume ratio or volume ratio. But for us, we're going to stick with the weight. Some examples of what's out there, you might find a lot of wines, for example, they talk about a percentage of alcohol. They're dealing with a volume percentage. And so that's an example where they use a percentage out there in the market. But we're going to stick with the weight percent. Then the second type of concentration, which we're going to use in the lab, by the way, on Friday, deals with molarity. Molarity is a ratio of moles per volume, specifically liters. Okay, so we have moles divided by volume in liters, and that is classified as molarity. We introduced this concentration back when we were doing the pH. Okay, we needed to know the pH was a negative log of the proton concentration. All right, so anyway, we're going to need to learn to calculate moles, and then the volume, if it's not in liters, we need to convert that to liters. Keep it in mind that most of the time we have 1,000 milliliters is equal to 1 liter for that conversion factor. And the moles is basically, we're going to be given a weight of a compound divided by the molar mass gives us the moles, okay? So we need to figure out what the molar mass is for a particular compound. All right, so let's talk about mass percent. Well, mass percent is a percentage of the mass of the solute divided by the mass of the solution. Now, this is where it can get confusing at times for students, in that the solution is the sum of the solute plus the sum of the solvent. It's all of it combined. So if you have an X amount of solute and you divide it by an X amount of solution, you need to divide it by, add the weight of the solute to the solution, okay? All right, for example, they're asking here to calculate the mass percent if you took 15 grams of potassium nitrate, okay, and we dissolved it in 135 grams of water. Okay, here we're not, when you deal with mass percent, we don't really care about moles or anything like that. We're not talking about that. We don't need to know more mass. You're given the amounts of solvent and amounts of solute. So you simply add the 135 plus the 115, okay? And that is the mass of the solution. You take 15 divided by the mass solution times 100. You end up with a 10% by weight solution, okay? And you qualify that, so you have 10% by weight solution. Because like I stated, sometimes you have a weight, sometimes you have a weight volume, and sometimes you have a volume percentage, which will all be a little bit different, okay? And so because of that, we're just sticking with the weight. All right. In this example, it was straightforward. You're given the solute, you're given the solvent quantity, calculate the mass percent. There are times when that's not the case. You are asked to determine the quantity, the amount of water needed to make a 5% solution. Now keep in mind, the mass of the solute, let me write this again. The mass of the solute divided by the mass of the solute plus the mass of the solution. That didn't come out very well. Okay, so just stick this under there. A lot of times you're given the mass of the solute, but you're not given the mass of the solvent, of the solution. And the solvent, so you need to calculate, this is the solvent, how much solvent you need to utilize to give you whatever percentage you're trying to calculate, okay? So keep this equation in mind to be able to answer the next question, okay? So here we have to set up that problem as an algebraic equation because they're telling us here we got to make a 5% solution of a salt. It doesn't make a difference what salt they're talking about. They just you got to be making 5%, and they're telling you you're going to take 10 grams of that material of the salt, taking 10 grams of it, and we need to know how many grams of water we need so that we have a 5% solution if we utilize 10 grams of salt. Another example you may, those who are nursing students, and you, or even if you're not, we have a 0.9 saline solution that is used a lot in the hospital, where it's just regular table salt, sodium chloride in water to make up a 0.9 percentage, which is utilizing liquid being put into you through intravenous systems, or you're mixing that in with medication. It's a 0.9 solution for a specific reason. And so your cells in your body won't explode or implode. Okay, but it's a different part of, we're not going to get into that. So anyway, just an example, 0.9 saline solution. So here we need to figure out X. X is equal to the weight of water. And so basically we have an algebraic expression. We got to solve for X and determine how much water we need. And how much water we need, that we need to add 10 grams of a salt to give us a 5% solution. All right, so first thing we need to do is isolate X. Now, what they did here, like in most algebra expressions, there's some multiple ways to solve this equation. It's not the only way to solve it. This is just one way, okay? And so here, what they did was basically take the quantity 10 plus X and multiply both sides by the quantity 10 plus X on both sides of the equation. Okay, that causes this to cancel out the denominator, leaving us with 10 times 100. And then we moved over 10 plus X on this side. That's how they got it in that direction. Now, at this point, you can do a multiple things to go from here. We're going to follow what the book does. And all they did was just multiply 10 times 100. That's 1,000. Okay. Then they went ahead and took that 5 and divided both sides of the equation by 5. And in doing so, cancels that out, isolating 10 plus X equals 1,000 divided by 5. Okay. Then 1,000 divided by 5 is 200. Now you have 10 plus X equals 200. All you got to do now is isolate X, and you end up with this number. Now, how they did that was straightforward, is they subtracted 10 on both sides. Okay, that cancels that 10, leaving you with X is equal to 200 minus 10, which is equal to 190. Okay. Now, the reason they put it into scientific notation is because of the sig figs. 3 sig figs, 5.00, this comes from a measurement. 10 grams is a measurement, so your answer should have this. This is not a measurement, it's 100 to give you the percentage. So both 10.0 and 5.00 have 3 sig figs. And writing 190 with 3 sig figs, you can't do it unless you put it into scientific notation. So writing it in that form, 1.90 times 10 to the second power gives you the answer in the correct number of sig figs. So yes, we do continue with sig figs throughout the semester. Here in science, sig figs are crucial. All right, so that is your answer. Basically, 190 grams of water are needed to dissolve 10 grams of salt, which in turn would give us a 10% solution. Okay, so the question is, how do you know that's the correct answer? Well, what you do is you go back and you check your answer. And you take that 190 and you plug that 190 back in here, okay, and solve it. So you go 190 plus 10, okay, that's 200. 10 divided by 190 times 100 gives you 5. 5 is equal to 5, which is a true statement. 5 is equal to 5, okay, which means that 90 is correct. If it would have come up with a different number other than 5 after plugging in the x, then first check your math, make sure you did the math correctly. And after you check the math, you know that's right, then what must be wrong is the answer, and go back and check your algebra. Okay. All right, so let me rehash here. What happens here is they're asking you to calculate the amount of water necessary to give you a 5% solution if you have 10 grams of salt. Could be any salt, to make a difference what it is. Not necessarily sodium chloride, could be anything you want to dissolve, and to give you a 5% solution. So we need to calculate how much water we needed. And so we came up with the algebraic equation, because by definition, the solute divided by the solution times 100 gives you the percentage. And the solution is the sum of the solute plus the solvent. Okay. Once we did that, we set it up for X for the quantity of water, solve for X, took the value X, 190, plugged it back into the calculator, to the equation, and verify that that is the correct answer. And it was in this case. All right. So you take 190 grams of water, 10 grams of salt, mix it up, you have a 5% solution, 5.00% solution. Okay, which brings us to molarity, okay? Now, think about this. When we do the lab on Friday, you're going to be dealing with a solution that has a certain concentration in moles and molarity. And that unit here, moles per liter, okay, if I multiply that by liters cancel, I'm given units of moles. So if I have a solution, for example, that has a specific molarity, and I take out a certain volume of that solution, I can calculate how many moles I have based on the concentration of that solution and the quantity of that solution that I utilize. So that's something that we're going to do on Friday in the experiment. All right, so here we have moles per liter. And how do we calculate moles per liter? Well, we first need to know the moles and then the volume in liters of the solute, the moles of the solute, and then the volume of the solution, okay? All right, so the question is here, is calculate the molarity if let me check my calculate the molarity if 9.99 grams of potassium bromide is dissolved in water to make 2.5 liters of solution. Okay, so what we're doing is we're taking potassium bromide. So we're given the name of the compound. We need to write the formula correctly. Why? Because we need to determine the correct molar mass. And we need the molar mass for potassium bromide so that we can calculate the number of moles of potassium bromide we have if we weigh out 9.99 grams of potassium bromide. So we can write the formula. Potassium has a +1 charge as an ion. It's in group 1. Okay, the bromide's in group 7, which when it becomes ionic has a -1 charge. So now that I got the elements here into ionic form, I can put them together to write the correct formula, and I can put them together on a one-to-one basis. Okay, so the formula is KBr. All right, now let's figure out the molar mass. Potassium is at 39.10 grams per mole, and the bromide is at 79.90 grams per mole. That's from the atomic weights. So the molar mass for potassium bromide is 0, 10, 18, and 19. So we got 10, 11, 119.00 grams per mole. That is the molar mass of potassium bromide. Okay. All right, let's clear this up. And we're in the volume of liters already, so we don't have to convert that unit of liters into anything else because we're already in it. So here we go, 9.99 grams divided by the molar mass of potassium bromide. Note that the grams cancel, leaves us with 0.08397. Now, use don't truncate, don't round up anything until the end, because your answer is based on the numbers you've been given. It's 9.99, which has 3 sig figs, and 2.50, which has 3 sig figs. So your answer should have no more than 3 sig figs, okay? And so don't truncate anything until the end. So you have 0.08395 moles of potassium bromide if you weigh out 9.99 grams. You divide that by 2.50 liters, and the molarity for this solution is 0.0336 moles per liter. That is the molarity of that. And we're going to do on Friday a solution of sodium hydroxide that we're going to use X amount with a very specific molarity, and we're going to do some experimentation. And from the volume that we utilize, we're able to calculate how many moles of sodium hydroxide we utilized. Okay. All right. So there's practice worksheets. Do those. Okay. We have the more practice you do, the more confident you get in these calculations. All right, move this up here for a second. All right, so let's try this one. One more. Calculate the molarity of 5 grams of sodium phosphate. If you got 5.0 grams of sodium phosphate is dissolved to make 255 milliliters of solution, okay? And so we're given the formula sodium phosphate which means we need to write the formula first. We have sodium, which we know is a group 1 element metal, has a +1 charge. Phosphate sends you to the polyatomic ion table, which has a formula of PO4 -3, which means we need 3 sodiums for every phosphate. So its formula is Na3PO4, okay? So the molar mass, we need to add up the atomic weights from 3 sodiums, 1 phosphorus, and 4 oxygens, okay? Second thing, we're in the units of 255 milliliters. So we need to convert that to liters. So remember that there are 1,000 milliliters is equal to 1 liter. So we're going to need this conversion factor to get that converted, the volume converted to liters. All right. Oh, let me clear this up a little bit, sir. All right, so once we get the formula Na3PO4, we find that its molar mass is equal to 163.94 grams, okay? And keep note here, these are the measurements that were given. So we have 2 sig figs here and 3 sig figs. Remember that our answer should not be more accurate than the least accurate number that we started off with, and that would be the 5.0 grams, meaning that our answer should have no more than, our final answer should have no more than 2 sig figs. All right, so we don't truncate anything here, round anything up until we're done with all the math. All right, so the next is to convert the 255 milliliters into liters, which is equal to 0.255 liters. Okay, then we do the math. Okay, keep it in mind that even though the numerator has all the digits, we started off with 2 sig figs. So our answer should have no more than 2 sig figs. So to rehash here, if you weigh out 5.0 grams of sodium phosphate, and then you dissolve it in with 255 milliliters of solution, in this case water, okay, you have a concentration or a molarity of 0.12 moles per liter. Okay. All right, so remember, you need to know from the name, you got to figure out the formula. From the formula, you can add up determine the molar mass, which is that number. So the weight given divided by the molar mass gives us moles of sodium phosphate. And then the volume of solution could be already in liters or not, but whatever the case, you convert it to liters. Then just divide the moles per the liters and you have molarity. All right, well, congratulations. Guess what? You are done. All right, there is a practice final exam on the website. I put that in the module. You might look that up to help you out, give you another resource. Other than that, we are done with all the chapters. I'm open up to any questions if you want. We still have some time left here, but if not, I'll see you on Friday, and we'll do the